It's to cloud. Okay, strange. Okay, so yes, as I said before, I think I should have gone through this in last Thursday, but initially I didn't expect that you will see a lot of problem in this one, but I did get a lot of questions during the weekend about homework, so I think it's worth spending a few minutes to quickly go through this, especially clarifying a few concepts. So once those things are clear, I think this is very straightforward. So this homework only have two problems. First one is about alloy solidification. It might be a little while since we discussed this case, but the idea is not difficult. This is about the case 3, right? So in this case, we assume that a steady state solidification at temperature T3. This means that if you look at the composition profile in the bar, right, we're always working with a bar like that, right? So this is a composition profile if this is X. So this is going to be my X naught, okay? So this line going to be my X naught, and suppose this part is solid and this part is liquid. We know that the solidification start with a fairly low composition, which is Kx naught, right? This is where you start, but quickly, because you cool the system to T3, it quickly go, as long as it went through this transition regime, the composition going to become X naught because you're, kind of solidifying the system at this temperature, and locally, the equilibrium composition for solid is going to be X naught, right? So except for a very short initial transient region, the system in the composition of solid is going to be X naught. Okay, but we know that because locally the solid and liquid are always going to be in equilibrium, so at the solidification front, because the current temperature is at T3, so the liquid is going to have a composition of X naught over K, right? K is the ratio between XS over XL for the entire solidification range. And we assume there's diffusional mixing in the liquid. This means that, this extra amount of solutes won't be, uniformly distributed in liquid. Okay, it's only going to be taken away by diffusion. So far away from the solidification front, the liquid is going to have the same composition X naught as you start which is the initial composition of the system. But immediately near the solidification front, you're going to have X naught over K as your liquid composition, and then this composition slowly decay to the far field value X naught. This is going to be the composition profile in our system, right? And then this profile in here, basically I said, okay, so if you solve the diffusion equation, which we don't have to, and you should get the composition of the liquid, which is basically this profile, given by this equation. And X is basically the distance away from the solidification front. So at this particular solidification front, you have X equals to 0. Okay, and this is going to be where we're going to start. Okay, so with this, I think you're quite clear how we, should answer these questions. The first one is to determine the concentration of a liquid, number one, right at the solidification front. So you just need to plug in X equals to 0 in this equation. And if you do the very simple algebra correctly, you should get the liquid composition right at the solidification front should equals to X naught over K, right, which is the equilibrium value predicted by the phase diagram. And when X is very far away from solidification front in this end, you should get the far field value. So when you plug in X goes to infinity, you get X naught, which is quite consistent with our qualitative analysis here. And based on these calculations, does the liquid in equilibrium with the solid phase? Yes, right, because it's right in the solidification front, the liquid composition is the actual equilibrium composition you should get from the phase diagram. So this indicates that the liquid, at least locally, is in equilibrium with the solid. Derive the flux of atoms repelled by the solid at the solidification front. Okay, so what is this? So basically, because we know that in order for this, because if you look at the incremental solidification processes, I think I have to speed up a little bit. So we convert a very, very small thin layer of liquid into the solid, right? But you see, the key thing here is that in order for this layer of liquid to solidify into solid, it has to reduce the composition. This means that during the solidification processes, right, certain amount of solutes has to be repelled in this small region, okay, into the liquid, because they have to reduce the composition in this region in order for the solid to propagate. Okay, so this means that the liquid region in the field of flux is a constant flux if you have a steady state solidification, right? From the due to the atoms repelled by the solid. So that is the physical origin of the flux, where that comes from, right? But the thing is that we don't have to. This is just the physical picture of what's going on here. But the interesting thing is that we don't have to start from scratch to solve this flux, because the flux due to the repel of the solid phase is the same flux, the incoming flux taken by the liquid phase. Now we don't know what is the flux repelled by the solid, but we do know what is the incoming flux taken by the solid, right? Because by the liquid, because we have this equation that describes the steady state profile of the composition of the liquid, and if you do a derivative of this XL with respect to x, okay, and get the value for that derivative at x equals 0, this basically allows you to compute the flux. So this flux simply equals to given by the Fick's first law, the diffusivity, right? And you have partial XL over partial X. Okay, so here you do not confuse with XL, which is the liquid composition, and this X is a distance. And then you basically evaluate this derivative at x equals 0. And that's going to give you the flux, okay, which is very straightforward. Okay, so now part C, okay, once you have the flux, this part actually ask you to check the conservation equation. So there are two ways that you can do the conservation equation. The first one is that we know the atom repelled, is basically can be written as flux times area times dt. So this is during time dt over this area, how much atoms has been repelled, right? So, and this should equals, no, this is the atoms taken, this is the atom repelled based on the flux calculation or taken away by the liquid. Okay, this should equals to the difference of the composition, XL minus XS. This is the contrast, the difference of the composition, right? A times dx. Okay, dx is the propagation of the solidification friend during time dt. This is the volume. This is the difference of the compositions. Overall, this is by definition the number of atoms repelled by converting a small amount of liquid into the solid. Okay, conservation equation implies that these two should equals to one another. And if you basically plug in what you obtain from this calculation, okay, and this part you don't have to calculate anything, you just need to use x naught over k and x naught. You see that these two equations check with one another. And if you simplify, you should get v on the left-hand side and v on the right-hand side. Okay, so basically this means conservation equation totally works here. Okay, that's for C. And for D is also not too difficult. Basically, this is about compositional supercooling, because we already talked about. So basically, what is compositional supercooling? This means if you map the equilibrium temperature profile, right? The temperature in the liquid depends on the composition. So basically, this is the temperature. Okay, you know that it gives you how the temperature depends on the composition, and you know the composition profile, so you can directly plug this in here. So you get the equilibrium composition temperature profile as a function of x, right? We know that if you this is the equilibrium case, right? So if your actual temperature profile is going like this, well, this means that all this liquid in this region under supercooling, because the temperature required to stable these liquids are not met, right? So you have a temperature which is lower than the minimal temperature required to stabilize the liquid. So we know in those cases, the liquid is not stable. It wants to transform into solid. You see a lot of unsteady growth. But on the other hand, right, if your imposed temperature field is like that, okay, you have a very fast increase of temperature right in front of the solidification front. Okay, all the liquids are happy because they're overheated compared to the minimum temperature required for them to be stable. So in those cases, there will be no compositional supercooling, and then dendritic will not form. So the condition that we derived in class is that you get this from the derivative, right? At x equals to 0, for example, this one. So at the solidification front, you simply take the derivative of this temperature profile, right? You basically take dt dx, okay? And then you make sure that the imposed temperature profile can be larger than this gradient. And then this will be the condition for no compositional supercooling. Okay, so for the sake of time, I'll just stop here about the homework because the eutactic question I think is straightforward. I didn't have a lot of question on this one, so I get a lot of question on the first one. So that's why I think it's worth spending the time to go through, quickly go through this. Okay, but again, I don't think there's any very tricks here. We just need to apply what we discussed in the class. I think then we should be able to solve this. Okay, so let me continue our discussion on the nucleation problem. So in the last lecture, if you still remember, we started to talk about precipitation and especially nucleation of precipitations, right? So we basically showed and discussed a different type of precipitation, nucleation, and mentioned that typically these, growing a secondary solid phase in another phase, solid phase field, typically, coupled a lot with the defects in the system. And we discussed the homogeneous nucleation, which means that you insert a secondary solid phase particle in the bulk of a grain of a parent phase field. So this means that you have to insert this yellow solid into the blue one, and this will cause a huge strain energy difference. And this is basically diminishes your driving force for the transformation. Okay, and then we move on to talk about another scenario, which is the heterogeneous nucleation. And in particular, we focus on the case when a small embryo of the second phase particle that form on the green boundary between two alpha phase. Okay, so basically this is what we have. This is a very local picture. Okay, so let me try to find a realistic picture for you. So for example, what I'm looking at is very like something like that. Okay, so these are, you probably wouldn't be able to see the grains, but you definitely see the, some of the green boundary features, like these are small grains, these large grains. So all these black things, they're actually nucleate on the green boundary, right? We didn't see the grains because this is just a optical image. We didn't see the EBSD contrast, but we're looking at something like here. So this is alpha grain, this is alpha grain. So this one is forming on the green boundary. So and for as in the case for the heterogeneous nucleation in the liquid solid transformation case, what we're interested in is that we want to compare how does heterogeneous nucleation reduce the energy barrier for the system, and is there any relation between homogeneous nucleation and heterogeneous nucleation? Okay, so the interesting thing for this one, why I'm still mentioning this, is that because this setup is different, or the shape of the embryo is different in the solid transformation case than from the liquid solid transformation case. In the liquid solid transformation, we have half of this guy, right? It's just a one spherical cape. But in this case, because the solid phase can basically go into both the alpha phase on the top and on the bottom, so we actually have two spherical cape. And we glue them together. We have this. I don't know what the best way to derive this. Sometimes we call this a lens-shaped embryo. Okay, it's very much like a lens. So it has a top part and bottom part. Okay, it's all symmetric. Have this, inversion plane here. This is the basic shape. So the idea is that, okay, if we have this particular embryo, what is the free energy reduction and it looks like? What will be the energy barrier? Okay, so to work out the mathematics, again, we first need to write down the balance of the surface tension at this point. Okay, so in this case, it's very straightforward. We don't have extra lot of terms. We'll just have the alpha surface tension or grain boundary energy, which tries to pull this point to the left, right? It wants to minimize the alpha and alpha grain boundary. And then we have the alpha beta interfacial energy, which try to pull in this direction along the tangent because they want to minimize the surface of alpha and beta interface. So, but these forces are at the balance at this point, and we're only interested in the horizontal component. If you write down that, you can easily get this relation. Okay, so in this case, we can work out what is the equilibrium value for theta, given the interfacial energy value for alpha grain boundary and alpha beta interface. Okay, so so this is kind of the first initial consideration. So the geometrical quantity now is related to the interfacial energy terms. Okay, so now if we consider that this part is the spherical cape and this part is the spherical cape, we can write down the very easily the free energy reduction due to the nucleation of this beta phase. Okay, so here, okay, I want to point out is that because we're on the green boundary, okay, we assume that in this case, and when the nucleus is very small, because green boundary already contain a lot of defects, especially these large, stacking faults and a lot of vacancies. There will be calculations and some experimental data, but many calculation results suggest that in this case, if the embryo is very small, basically if you form an embryo on the green boundary, it won't cause a lot of strain energy. So in our treatment, we just take out that strain energy increase term. We assume that this is your bulk free energy reduction, and then you won't have any issue with the strain energy because you're forming a small embryo in the green boundary. Okay, so this is the only bulk term, which is the driving force. And then you have clearly this one is the creation of alpha beta interface. So you have this additional term, and A alpha beta refers to the total surface area. It's not only one half of these guys is the total surface area, including this part and that part. Okay, so this is A alpha beta, and A alpha alpha is simply this area, which we didn't show. So is this circular area, okay, which is taken by the beta phase. But before you grow the beta phase here, it has this alpha alpha green boundary. So basically, when you have this beta phase here, you basically eat up that part of the green boundary, so it reduces the alpha alpha interfacial energy. So that's why I have a minus sign here. But the idea is very straightforward. We'll just list all the terms for the driving force and the barrier, and consider the possible changes due to the formation of the nucleus. And when we have that, and assuming that we have the spherical, yes, this is as I said, that the green boundary additional strain energy cost is very small, so we simply ignore that. If we assume that this is a spherical cape, we can simply use the same mathematics that you went through in homework 3. And the reason why I went through is that you see this can come back again in many of the heterogeneous nucleation cases. So it worth working out the details at least once. Okay, so we just plug in the mass, which I want to be able to show here because it's extremely similar to what we did before. So we get these results, which again is quite familiar. So basically, if we compare the homogeneous nucleation to the heterogeneous nucleation case, we basically can see that these two nucleation cases have virtually the same expression, except for factor depend only on theta, which is the angle that defined by the surface energy terms, right? And this theta has a slightly different form, I believe, compared to the liquid solid heterogeneous nucleation. But the key point is that this theta is also has the value between 0 and 1. Okay, so it doesn't really matter what is the value for the free energy, the interfacial energy. This value is going to always be between 0 and 1. So compared to the homogeneous nucleation, you're always going to get a reduction of the energy barrier, okay, for the nucleation, okay. But the also you get a slightly different change of R star, which is the critical nucleus, because in this case, you didn't have the extra term for this strain energy difference. If you remember that for the homogeneous nucleation, we have a strain energy term, okay, which is also in this denominator, but in here, because we're on the green boundary, so we wouldn't have this term. Okay, so that's basically the difference. But anyway, so the insights are basically the same as we had before. So basically, heterogeneous nucleation is much more easier compared to homogeneous nucleation because we have a much lower free energy barrier. So it's much easier for you to nucleate using the heterogeneous mechanism. And this is exactly what we see actually in the actual material system. Yes, I already have that. So, okay, so for the same consideration, we have the nucleation rate, but again, this nucleation rate is key factor to determine the nucleation rate is this guy, which is the, the critical energy barrier. And if you take the ratio between the two, you'll see that the nucleation rate for the two cases is basically the ratio between the two is determined by this exponential factor, depending on the difference between the barrier for the nucleation. Okay, but the key thing I want to show you here is that this is our from our analysis we come to the conclusion that heterogeneous nucleation is clearly more frequently occur and more easily to occur in the system. Okay, and I think we have a lot of evidence for this conclusion. Okay, here I'm just showing you one of such evidence. So this is a stainless steel, I guess, or just simply high carbon steel image. Okay, and this is the um, basically the scale showing you the bar scale bar showing you the size of this material sample, so it's not very large. And what we see here is that the two different phases. Okay, the austenite is the alpha, I think, the gamma phase of almost pure iron, and the ferrite is the iron combining with carbon. Okay, so it's a different phase. Okay, so this ferrite is the secondary phase that precipitates if we lower the temperature. So it basically plays the same role as beta phase in our previous analysis. And what you can clearly see here is that, although we didn't show the grain structures for the austenite, but you can basically from these plots, right? It's quite clear that most of the ferrite are actually on the grain boundary. Okay. What you see here is not the initial stage of the nucleation. It's already at room temperature. So, what you see are large amount of ferrite phase, which basically all grow along the grain boundary. So from this image, you can basically trace what the grains look like without using EBSD, right? Because all the ferrite phase, they actually grow along the grain boundary. They form on the grain boundary, just maybe a triple point, but they grow along the grain boundary. So, without even looking at the EBSD data, you can probably already see the shape of the grain and what the grain looks like. Okay, so this is kind of a very intuitive evidence indicating that the heterogeneous nucleation is much more frequently and much easier to occur in most of the solid-solid transformation. Okay, because after the transformation at room temperature, basically what we see is most of the secondary phase precipitates, they are on the grain boundaries, they grow along the grain boundary, they trace the grains. Okay, this indicates that they form on the grain boundary, and you won't see a lot of, probably this is a homogeneous nucleus, okay, and this is another one, and these ones are homogeneous nucleus. You do see these globular things, right? But they're very small. They won't grow a lot because of the strain energy constraint. But occasionally they do form within the grains. But I think the compared to the heterogeneous case, it's much rare and grows much slower. Okay, so that's pretty much all I want to say concerning the um, um, nucleation of the precipitation growth. Okay, again, we went through these concept of nucleation in solid-solid phase transformation. We talked about the homogeneous case and we talked about the heterogeneous case. And the key idea I think we get is that the heterogeneous nucleation is much more, more frequent in for these solid-solid transformation mechanism. Okay, and we'll see a immediate consequence for this. Okay, so that's about nucleation. Okay, I know that I go through this fairly quickly because I think there's not too much new concept added to this. It's like we're reveal the same concept, but apply, we already introduced, but now apply them to the case of solid transformation. Okay, so now let's keep on our processes. Okay, so what we have been focusing on is this particular branch, right, of the phase diagram. So if we choose a low composition alloy, we have analyzed the liquid solid transformation, and now we're, if we push into the even lower temperature regime, we're actually looking at the nucleation and growth of the precipitates. Right. In the last lecture and the beginning of this lecture, we spent a lot of time discussing the nucleation mechanisms, comparing the nucleation for this particular solid transformation to the liquid solid transformation, and we can appreciate the similarities and differences, but we and also get some insights, namely that for the precipitation growth, the heterogeneous nucleation, which means that the secondary phase particle grow on the grain boundary, is much more frequent. It's the key dominant mechanism for the precipitation growth. Okay, so now based on this insight today, we're going to discuss the growth of precipitates, okay, in solid-solid phase transformation. And because we already come to the conclusion that the green boundary nucleation, the heterogeneous nucleation on the green boundary is much more frequently and it's a dominant mechanism for the transformation. So we will just focus on this particular mechanism. We will not go back and talk about the growth for the homogeneous nucleus, right? Because we see from the previous image that they usually are very small, do not grow a lot, and in terms of numbers, these nucleus are much smaller, much rare to see. So we will focus on the dominant mechanism on the green boundary nucleation and see how, if we have a small embryo nucleated on the green boundary, how this thing gonna grow. Okay, and we'll see that Gibbs-Thompson effect also come to play. And in particular, we're going to talk about two different mechanisms for the growth. The first one is called thickening. As you can imagine, we have an embryo. So if this embryo basically grows thicker and thicker in the direction perpendicular to the green boundary, this is one way for them to grow. And the other one is through elongation. So they actually propagate along the green boundary. Okay. And without going through all the mathematics, I think you already have an impression from the image we show that the elongation is probably going to occur much faster than the thickening, right? Because you basically see that these black phase that they keep on growing on the green boundary and the traced green boundary. So the elongation growth is probably much faster. And this is indeed the case, as we'll show later of the lecture. Okay. Again, this is the second step in our discussion of solid-solid transformation or precipitation growth. So yes, this is the same picture I showed before, showing you the complexity of how the nucleation or the precipitates are coupled with different defects existing in the solid. And we focus on the green boundary nucleation, in this case, the growth of these small nucleus formed on the green boundary. Okay, so again, this is the image that we already see, right? So once you have a small nucleus formed on the green boundary, you can clear, this might be a small nucleus formed on the green boundary. It won't have a lot of time to grow. It may be formed in a later stage. But for most of the others, you see that they typically gonna elongate or grow along the green boundary, right? But another way it can grow is basically to expand in this direction, further expand into the two grains. And both of them are possible, right? There are two modes of growth. And from this image, I think we can clearly see the elongation is probably much faster than the perpendicular growth and the thickening, right? But still, we need to work out why this is the case and how these two are potentially coupled with one another. Okay, so this will be the major topic for the rest of the lecture. So now if we're clear that there will be two major ways for the precipitates to grow, we're just looking at them separately, assuming that these two are decoupled, which is reasonable in most material systems because the lengthening is much faster than the thickening. So you can consider that, when we talk about lengthening, the thickness can remain the same in certain sense, okay? But we can decouple these two growth modes and look at it separately. So we'll have thickening and we'll have a lengthening, right? Again, thickening means that the precipitates grow in the thickness direction. So they actually grow into the alpha grains on both sides. And for the lengthening, this means that the precipitates elongate along the green boundary, okay? So let's first look at thickening, okay? So if the idea for the thickening, I think, is pretty much the same as we already discussed for all of the alloy transformation cases. Okay, the key thing is that, and one thing I would like to point out is that, typically when we say a grain, like when we do this setup for getting the nucleus analysis, we place the embryo or the precipitates along the horizontal direction, okay? But when we talk about thickening, okay, we basically flip this, okay? And then, we consider our X direction is perpendicular to the green boundary, okay? So basically you have alpha grain here on this side and you have another alpha grain on this side, okay? So this is what we're looking at. And for mathematical convenience, the way how we do that is, because we know that this thing is shared by two alpha grains, right? One on the left and then one on the right. So basically we split this beta grain in half, okay? And we set our coordination system to be here. Okay, so this is gonna be the origin of my x-axis, gonna be in the middle plane of my beta grain. Okay, and also we're looking at a small portion of this beta grain, so we're considering that, you know, locally we consider this is kind of a flat thing. Okay, so that's our basically the simplification and setup for this mathematical problem. And now we're gonna assume that if I want to achieve a steady state thickening velocity v, okay, how the dynamics is going to play a role, okay, how conservation allow us to write down the equation for the steady state of velocity, okay, and from this point on, you'll see it's very familiar. So now the basic idea is the following, right? So suppose that we have a initial alpha grain, right, with a composition of x naught. This is our initial composition. And now I super cool, I quench the system to the temperature T2. And we know that in this temperature, the system wants to separate into two different phases, alpha plus beta, or in other words, you begin to see beta phase start to grow. Okay, or another way to understand this is that because you lower the temperature, so the alpha phase cannot, the solubility of B atoms decreases in the alpha phase. So the alpha phase cannot dissolve, you know, the large amount of beta B atoms. So the B atoms going to just precipitate out as a get clustered at a secondary phase. Okay, all these things are the same mechanism. So, but if you look at the composition, what happens is that initially you're going to have X naught, right? But then what happens is that some of the B atom is going to, you know, go from the original alpha phase, okay, all the way to this clustering of B atoms, which is the beta phase. And your alpha phase should have a slightly lower composition, which is Xe, okay? So initially, all the alpha phase is going to have X naught as the composition, right? And you know, if we cool the system, the equilibrium composition should be Xe, which is lower than X naught. However, this process is occurs through solid state diffusion. So as you can probably imagine, it's kind of a relatively slow processes, which means that in order for the beta phase to grow, what happens is that, you know, all of the original B atoms distributed in the alpha phase, which I using small dots here, hopefully you can see them, and B atoms in this alpha phase, right? And they have to really move to the green boundary, to the beta phase where they cluster, right? And all the B atoms are going to move to the green boundary to add to the beta phase, and then the beta phase is going to grow. Okay, so this is what's basically going on in the system. Okay, and when these extra amount of B atoms are moving away from the alpha phase, the consequence is that the alpha phase composition is going to get lower, and then going to approach the equilibrium value, which predicted by the phase diagram. Okay, so this is, you know, it tells you what's going on in of the kinetics of the system. Okay, now how this is going to help us in our analysis? Okay, so So again, the key thing is that once we understand this kinetic processes, we want to set up a composition profile. And then, you know, if we analyze the composition profile using the conservation equation, we should be able to get a steady state velocity for the system. Okay. So again, what we have here is that, okay, we use C versus X, but basically S is molar per mole. The molar fraction C is probably the number of atoms per unit volume. But these are the same thing. It's just you know, have a molar volume. That's the only difference. But these are basically the same concentration. They mean the same thing. Their values indicate the same level. The only difference is that they're scaled by a constant of molar volume. Okay, so in the later of the discussion, I will probably interchangeably using either C or X. But you know, we should keep in mind that these are the same thing. They're all the composition of the system, but expressed in different numbers. Okay, but anyway, so now based on our analysis here, right, we say that, you know, if you look at the composition in the alpha phase, far away from the solidification for the this beta alpha interface, we should have a composition of C naught, which is X naught, right? This means that very far away in the alpha grain, right, like in here, okay, you know, because this process is through diffusion, you know, all the B atoms are still remain there. It has not had the time to really move towards the alpha beta interface into the region where you have the transformation occur. Okay, so far away from that interface, this is the alpha beta interface. This region is the alpha phase, and this is the beta phase, and this is the alpha grain. Far away from the alpha beta interface, we have this C naught, which is the original composition that you set up for the system, right? And right immediately at the front, we cannot say the solidification front, but we can call this the transformation front. Okay, we're in equilibrium. So beta phase has the corresponding composition, which is X beta or C beta, okay, given by the phase diagram. And alpha phase also has the corresponding equilibrium composition, which is C equilibrium or X equilibrium. They're the same thing from the phase diagram. Okay, so this is what we have. And you clearly can see that, this CE is lower than C naught, okay, far away in the beta phase and the alpha phase, because the extra amount of B atoms is keep on taking by the beta phase in order for this precipitate to grow, right? And then because we have this composition, this gradient, so basically you see there will be a constant flux of B atoms, right, deep in the region of alpha phase from this region, to the alpha beta interface. And then once the B atoms reach the alpha beta interface, these atoms will be taken by the beta precipitates, added to the beta, as a part of beta phase. And then this process continues, so your beta phase can continuously grow. Okay, it's basically what happens to the system, okay, for the kinetics. Is this clear? Do we have any questions about these processes? Okay. So at this stage, I think we're very familiar. Once we reach this step, the next thing I will do is to write down a conservation equation, right? So now, but the interesting thing is that in all the previous conservation equation, the phase we're interested in going to repel solutes. But in this case, it's not repelling solutes. Okay, like for the beta phase to grow, it has to grasp the extra amount of B atoms in order for it to further propagate. So this is another kind of interesting difference between all the previous cases we're looking at, right? So in order for the beta phase to grow, you see it has to grab sufficient amount of B atoms in order to reach this composition, okay? So if the beta phase propagates a little bit by dx, right, during time dt, it has to grab sufficient amount of B atoms. And the only way how these B atoms can be transported to the interface between alpha and beta is through diffusion, okay? Now, again, this is a conservation equation, okay? And by considering this conservation of B atom, okay, we can actually set up an equation which looks very similar to what we did before, okay, but is in a different context, okay? So again, now I'm just keeping the composition profile and this schematic setup for the beta phase and alpha phase interface. So the condition for the, I'm sorry, this is, I think, a mistake. So it should not be the solutes repelled. Okay, it should be the solutes received or taken by the beta phase should equals to the amount of solutes, okay, flow to the interface by diffusion. Okay, because you have a constant flux of B atoms coming here, and these B atoms are taken by the beta phase. Okay, and in this processes, if you want this process to occur at a steady state rate, you have to make sure that this conservation equation is satisfied. Okay, so based on this consideration, we actually had this type of equation many times. Basically, this is the amount of solutes you have to take, okay, or receive by the beta phase in order for it to grow, right? This is your current composition for the alpha phase, and this is the composition for the beta phase. So the contrast times the volume will be the extra amount of solutes B atoms need to receive by the beta phase, right? And these atoms are provided through diffusion. Okay, so this is the flux times area times dt times diffusivity. This is basically the total atoms provided through diffusion, okay, to the interface, and the beta phase gonna take these atoms and then they further grow. Okay, so this is basically the conservation equation in this particular context. Okay, and so once we reach this step, the next step is very straightforward. Okay, what we need to do is simply use this conservation equation and simplify this a little bit, right? The area cancels one another. At this stage, we should be very familiar with this. We'll take a dt to the left and this part to the right, and this allows us to find a very interesting equation. Okay, so and here, it doesn't really matter whether you have the absolute value or not because the composition is increasing. So this derivative is going to be positive, but I'm here just to make sure that the velocity is positive, is propagating to the right. Okay, it is determined by a number of factors. The first one we see is always proportional to the composition gradient, right? The larger the gradient, the faster the transport, you're always going to get faster growth. And also it's linearly proportional to diffusivity, which is again a transport property. The faster the transport, the faster you can grow. Okay, and it's inversely proportional to the contrast. This means that you have, if the contrast is large, this means that you need more of extra B atoms. So it will take longer time for these atoms to arrive at the interface, and then it will take, basically slow down the growth. Okay, does this make sense to everyone? Just want to make sure this is clear. Okay, so in most cases that we'll just stop here, right? Once we have the velocity, we'll just stop here. But in this particular case, there's something very interesting that we could do, okay, about the system. The key thing is to realize that, the composition profile, like, this thing, okay, can be approximated using a very simple linear way, okay? So again, if you want to solve the diffusion equation, you could solve the diffusion equation. But the insights we obtained is pretty much what we describe here. Okay, we know that for this diffusion problem, a key quantity for this diffusive composition profile is a length scale, right? Typically, we call this diffusion length, over which the composition of the solute is gonna, the majority, the most dramatic change of the composition profile can occur within that distance. We call that diffusion length, right? So, and suppose that, and the actual value for this length is going to be determined by the diffusion equation. But let's, for now, suppose this is a constant, right? Its value is L, and then we can approximate the composition profile in the liquid also as a kind of a linear composition profile, okay? And due to the conservation of solutes. Now, this conservation of solutes is not for the case of the dynamic, is for the overall composition field, right? Because we know initially everything going to be C naught, right? So if we start the, from the alpha phase field, everything is going to be C naught. This is an equilibrium composition or average composition that we initially set up, right? And then you separate it into two phases, the solutes redistribute themselves. You have more solutes in the beta phase, less solutes in the alpha phase, but the total amount of solutes is conserved, in these processes. Now, the consequence of the overall is a global conservation of solutes is that, the actual amount of solutes in the beta phase compared to the initial solutes X naught, the total actual amount of solutes in this region, excuse me, have to equal to the solutes lost in the liquid, right? Because basically what happens is that the beta phase take extra amount of solutes in the liquid, so you have this more concentration of beta B atoms in the beta phase, but these two shaded areas should equals to one another, right? So this is kind of a global conservation of solutes. Okay, and this area is very easy to compute, right? X, basically, if you consider this is the thickness or a characteristic thickness of the beta phase, right? So X is basically the thickness, and we know if we assume an area A, the volume of this shaded region is simply X times A, right? I will show that equation later. Probably I didn't show that, but X times A is basically the volume, and then if you basically take the difference C beta minus C naught, okay, this is the total amount of solutes taken by the beta phase from the alpha phase, right? And this shaded area gives you the total loss of the solutes in the alpha phase. And also it's easy to do. We have a delta C naught, which is C naught minus CE, right? Which is the height for the triangle. And we have this L, which is the, bottom edge length, for example. So you can easily write down the the area for this shape, which is a half times L, times del C naught, okay? And then you times the area A. So this is the total amount of solutes lost by the liquid, and this two equals to one another, okay? Basically the shaded area equals to one another. And if you do that, you can actually get what is the concentration gradient, okay? Because the concentration gradient is simply delta C naught over L. Okay, this is all, why we're doing all of this. We just want to find a linear approximation of the concentration profile. Okay, so based on this, okay, I think we can easily write down. Yes, so this is basically the equation I just wrote down, but here is a nicer way. So we have this shaded area, which is given by this one. Okay, and we have this shaded area of the triangle, which is given by this one. And after you get this, you get what is the expression of C naught, delta C naught in terms of L and X, right? But the key thing is that, you once you plug this in and then get the based on this delta C naught, and you compute the derivative, okay, after some very simple algebraic rearrangement, we plug in the expression, which I don't have for you, but I will reserve a homework probably on this one for you to work out the math, which is very straightforward. Plug the expression that you get from here into the velocity expression we obtain. We have this very nice expression for the velocity. Okay, so the thing that I want to point out here is that so for a given supercooling, so delta C naught, basically, what is this delta C naught? Okay, I think I have some analysis for you later, probably not now. But if you go back to the phase diagram, you see this delta C naught, which is also, delta X, that's roughly the same thing, okay, is proportional to the supercooling. So the larger supercooling delta T you have, okay, the larger delta X you have. Okay, why is that? Let me quickly show you this. So basically, if I now have a larger supercooling delta T like here, right, and I will have a larger delta X, right? So this delta X or delta C, which is basically the difference between X naught and XE, or you convert in the case of this C to C naught minus CE, is proportional to supercooling. Okay, so in this sense, in our expression, basically you see the gross velocity, okay, the major driving force of the gross velocity is this delta C naught, which is proportional to delta T. And from this simple scaling relation, we can safely conclude that this gross velocity, okay, is proportional to the square of the degree of supercooling. Okay, and this is, again, it's very familiar relation you've seen many times. Okay, now another thing is that these two are just a constant. Diffusivity, we know the rule. Another thing is that you see the velocity, okay, the gross velocity in this particular case is inversely proportional to x. Okay, but what is x? X, as we noted here, is roughly speaking the thickness of this beta precipitates. Okay, this is something new, right? We've never seen this before in our previous analysis. So basically, what does this mean? Well, this means that, if initially you form the small nucleus, X is very small, right? It's very thin nucleus. Okay, in that case, the velocity is large, right? But as X grows larger and larger, because you're propagating the beta phase, you're adding more and more B atoms, so necessarily this thing gonna grow thicker and thicker, X gonna increase over time. So this means that X keep on increasing, the velocity is decreasing. Okay, so the growth of the precipitates of this particular beta plane, on the green boundary, in the thickness direction is slowing down as the thickness increase. Okay, so this is a very interesting feedback mechanism, right? We've never seen this behavior before in all our analysis. So we would like to, try to understand this a little bit more. Okay, so the next thing I would do is that, okay, I want to understand how this guy, okay, gonna affect the gross velocity. Okay, we know that this is kind of a inverse proportion relation, but can we write down something more intrinsic? Okay, it turned out, yes, we can write down that. The reason is the following, because if you look at what is velocity, what is this gross velocity? The gross velocity itself is dx dt, right? And x you can basically consider as the thickness. Dx is basically the increase of the thickness. So basically, if we do not use this as v, but use dx dt, okay, write down this here, what you have constructed is a first order ordinary differential equation of the thickness, right? And you can potentially solve this equation to get a function of x as a function of t, okay, which is very, very useful then. So this is what we're gonna do next, okay? Once we realize this, okay, we can basically plug in, v equals to dx over dt, right? And if we basically plug in that equation in here, we get dx over dt equals to this whole thing, right? It may be complicated, it may be related to the driving force diffusivity and the compositions, but for a given supercooling, this whole thing is a large constant, okay? This whole thing is a constant, right? Basically what we have is equation of dx dt equals to some constant times 1 over x. Okay, does this make sense to everyone? So the equation seems to be complicated, but if you just consider the whole thing as a constant, it's very simple. Okay, differential equation, ordinary differential equation connecting x, which is the thickness of the beta precipitates, and t, which is time. Okay, and we surely know how to solve this, right? This is very simple, and we just move x here, move t here, and we can integrate on both sides of the equation. Okay, and the integration is very straightforward. Basically, what we get. Okay, so we basically solve this equation. Okay, one more thing we're gonna do is that if we look at this expression down here, okay, so we have c beta minus ce, and here we have a c beta minus c naught. Okay. And from the phase diagram, if we saw here, I'm going back to the phase diagram. Okay, so if in this case, we're already actually make it quite distinct because we're looking at the local region in here. But in the real phase diagram, x naught and xe are typically very close to one another, especially when delta t is small, and x beta is very close to 1. Okay, so x beta is much larger than the difference of these two things. So this allows us to make a approximation that we can simply consider these two terms equals to one another. Okay, and we can simply replace the CE with C naught or C naught with CE. The reason why is that then we can take the whole term out of the a square. I'm sorry, a square root that we're need to deal with in the solution. So so basically what we have here is that, so if you rearrange the terms, I don't think I have a derivation for you, but it's very straightforward. We rearrange the terms. Basically, you get x, right? This is going to be dx. I think there's a factor of 2. I can't remember, probably here. And then in this part, I have a constant times dt, right? And if you can look at this one, this is basically d x squared. And then this is d some constant times t, right? And there may be some constant, but basically the integration on the left side and on the right side basically allows you to obtain something of x squared is proportional to some constant times t. I'm sorry, there should be no square root. So x squared is proportional to some constant times t, right? But if you take the square root on both sides, you get x is proportional to, a constant times square root of t. Okay, this is what you get. Okay, and now basically if we do this more rigorously and then do what we said, we change c and back to x. This should be capital X, but you get the idea. So this is the composition. This x naught is simply equals to delta x naught is simply equals to, I'm sorry, it's not like this, is x naught minus xe. Okay, this is the contrast of composition. Okay, in the alpha phase, we'll do the supercooling. Okay, so yes.
Dx square is proportional to dt, right?
The x square proportional to dt. So if you do the integration on both sides, you get basically the differential thing out. So basically you get x squared proportional to t, right? And there, well, I'm not showing that there's a constant, of course. somewhere, but I'm just showing the key functional relation between these two factors. There will be some constant which we'll deal later. But is that clear? Okay. So yes. So basically, this gonna, after solving this equation, we can get this relation between x, which again is the thickness of the beta precipitates as a function of time. Okay. So again, this part, it would just be a constant related to the condensation, which is also related to the supercooling. But again, for fixed supercooling, we don't have to worry about this first term. Okay, the only thing we need to know is that there is a factor that play as a role of driving force for the supercooling. If you have a larger delta T, you're gonna have larger delta X naught, which means that your X is gonna grow faster. But the key thing is this, okay? So the key thing is that if you look at the X, which is length scale, right? So this means that the length scale grow as a function of time looks as if this is just a diffusion distance traveled by the particles. So in other words, we call this type of dynamics is diffusion controlled. Means that you have a length scale, for example, you have the thickness of the beta precipitates. The increase of the thickness, the growth of the thickness is scaling with the time as if this is the diffusion processes and the particles are taking, diffusive dynamics, and X is effectively the diffusion distance. Okay, so we call this the diffusion controlled processes. The question is that why this is the case? Right? Why in this case we have the length scale, which is basically determined by the diffusive dynamics? Well, if you consider what we described in the beginning, right? Consider what is the mechanism that caused the beta phase to grow. Okay, is if you think about that, it wouldn't be difficult to see because the key dynamics determine how fast the beta precipitates can do this thickening is how fast these extra amount of B atoms, which I'm showing here using small dots, can transport to this alpha beta interface and add it to the beta phase, right? But what is the key dynamics or kinetics determine the transport of these extra B atoms in the alpha phase? These B atoms transport to the beta through diffusion, right? So how fast the beta phase can grow, depending on how fast these B atoms can transport, and these B atoms transport through diffusion. Okay, so that's basically, if you want to find a physical rationale for this relation, that's basically the reason. Okay, so it's not directly related to the diffusion distance of B atoms, but it's governed by the same dynamics. Okay, so that's why you see this scaling relation. Okay, so it's quite cool and very interesting. And as you can see, what is the functional forms for square root of time t? Okay, it grows initially very fast, but eventually gets slower and slower and slower, right? So this is basically how this function looks like. So this is the increase of x as a function of time t. Okay, initially it grows pretty faster, okay? And then as time becomes larger and larger, the growth is slowing down. Okay, so this is for x, right? We solve for this very nice equation to find a relation between x and t, but don't forget our initial idea is to find what is the relation of v as a function of t as well. Well, there are different ways you can get that. Okay, I think the easiest thing is that based on the definition, v equals to dx over dt, right? So what you need to do is just to take the derivative of this guy, okay, with respect to time, and then you can have an expression for the velocity, which is also very straightforward. Okay, so if you do that, okay, this is the expression for the velocity. You see that the first, I think we're missing something, but again, the first this part is just a factor. It's kind of a constant. If we fix supercooling, the key thing we're interested in is the scaling behavior in here. Okay, so for the velocity already, as we already mentioned, that if we look at original equation like here, okay, for large x, we know you get smaller velocity. This means that as x increases, the velocity is decreasing, right? So now we see an even clearer relation between velocity and time t, right? Time t basically is more intrinsic than x. So this means that, initially the velocity may be very large for small t, but as t increases, you see is basically inversely scale with the t square root of t. So for larger and larger t, the velocity is going to get smaller and smaller and smaller. Okay, eventually the velocity is going to equals to 0, and the propagation will stop. Okay, that's the asymptotic long time limits. But the reality is that way before we get to this point, okay, we stop the dynamics. So this thickening process is typically very, very slow. Okay, for most of the time, we won't have, really the patient to wait until the atoms, they all diffuse to the interface, and wait naturally for this process to stop. For most cases, we just quench the system, and then stop there. So it basically the actual dynamics stop way before it naturally stopped based on these diffusion dynamics. Okay, so I think that pretty much all I want to tell you for this lecture. Okay, we spend a lot of time describing this very interesting mode for the thickening growth. Okay, and we see that this is a diffusion controlled processes. Okay, and in the sense that the thickness of the plate of the beta precipitates grow as time via the same relation of how diffusive particle transport far away from an initial origin. So this is the same scaling that we see of the diffusion distance, right? So we call this process diffusion control for the reason that we already explained. And in terms of velocity, we see in this case, as x increase, velocity decrease, and in particular, the velocity going to decrease or inversely scale with the square root of time. So towards the very large limit, velocity going to get zero or very close to zero. So the thickening going to stop naturally. This is again because of the diffusion process also going to stop for a long time in the long time limit. Okay, so so that's pretty much all I want to say about this case. Yes, here are some insights which already went through. So the growth diffusion, the growth is diffusion controlled. So we have this particular scaling relation, and the growth is quickly slowing down as t increases. So basically, all the thickness that you see from this original image that we show in the beginning of the lecture is pretty much due to the very first few initial few, I don't know what is the time scale, maybe hours, few hours, a few minutes of growth for the thickening of the plates. Okay, after that time, the growth will be very, very slow. So we will see quite change of the thickness. Okay, so that's for the thickening. So as I said before, I'll stop earlier. So I'll stop here. Okay, and in the next lecture, we'll continue our discussion on the other mode of the precipitate growth, which is lengthening. Okay, as you can probably imagine, the lengthening will involve a different mechanism than the thickening, right? So lengthening is also the key thing for the lengthening is, again, we have to add B atoms to the precipitates. But the question is that where do we add the B atoms in the case of lengthening? What is the difference between lengthening and thickening? What is the kinetics, the mechanisms for kinetics for adding these B atoms to the precipitates, and how this will make a difference between lengthening and thickening? These are the questions we're going to focus on for, I think, lecture on Thursday. Okay, so with that, I will just stop, and I'll stop recording.